Everyone. Thanks for got it. Thanks everyone. Thanks for having me. And yeah, I was super surprised and very thankful to receive that award last year. So I've been almost 2 years out of my PhD, and when I was doing my PhD research, I had my nose stuck on the problem, and I don't think I fully realized what was the implication of my work. When I started working in Yukon territory, I thought I was starting from zero, mostly because the saline basin is low metamorphic grade and there's no shear zone, it's all faults. But then after doing a lot of field work, I started realizing that a lot of the concepts that I learned during my PhD are applicable to the Canadian Cordillera. And I thought it'd be worthwhile to revisit my PhD work in that light. So we'll start by looking at individual shear zones in the Canadian Appellation, and we'll put them together into what I think is a shear zone system that's coherent. And from that, we'll interpret a regional tectonic model using regional geophysics. And at the end of that portion of the talk, we'll move on to what I'm doing currently for my postdoc. It's mostly economic geology, but there's some of it that's regional tectonics that I think ties in directly to the Canadian Appellation. So the Canadian Appellation is an accretionary orogen, which means that several terrains were accreted through time on the margin of Laurentia. When I say Laurentia, I mean North America. So that's basically well, basically anything that's behind the Appalachian front here in dark blue. Each of these continents or terrains, when they were accreted, they created an orogen or regional deformation event that are known as tectonic, salinic, Acadian, and Neo-Acadian. And each of these deformation events reactivated and formed new structures inward of their suture. So each of these dark lines on the map here is a suture that's related to the collision of a terrain or small continent. And the overlay, so the colored in yellow and orange and green, correspond to the extent of the deformation, at least what we thought was the extent of the deformation before I started my PhD project. So initially we set out to work on the Cape Breton Island, and we thought that the deformation there was related to the Acadian orogeny in yellow, and that the Neo-Acadian deformation related to the collision of Meguma in orange was mostly restricted to the suture zone and the Quebecois-Chedeboucto shear zone in orange, and also to the Meguma terrain here. But we quickly realized that that's not the case. So there was already some really good work done on the Eastern Island shear zone by Chouffalin for his PhD thesis. We already knew that there were two deformation events, D1 and D2, and we set out to characterize and map these fabrics along that shear zone. And if we consider only the reactivation of the Eastern Island shear zone, so the D2 fabric, we're looking at subvertical to oblique mineral lineation and a steep myelinite fabric that's oriented north-south or northeast-southwest, depending on the segment we're looking at. The rocks involved are pretty deformed. So for example, in the upper left, there's a metaconglomerate, but in this case, you can barely make out the clasts. It's very strong monazite. There's a rhyolite unit, an altered granitoid, and that altered granitoid on the margin of the Eastern shear zone is often brecciated. So it transitioned from a myelinite to a fault zone. And that's also a common theme in the Appellation in general. Now, when we sampled the Eastern Island shear zone, we focused on the quartz-rich lithologies, or the quartz-rich portion of the lithologies, and we sampled regularly across the shear zone to establish what we thought would give us on the deformation gradient. Didn't work out so well, but what we found is that the quartz grains were oriented in the way we initially supposed. So I need to give you a little bit of background information on that. So when I show steronets here with a mineral lineation, we interpret generally the kinematics with respect to the mineral lineation in a shear zone because we think that the deformation is related to a monoclinic general shear environment. That means that the relative motion across the shear zone is parallel to that mineral lineation. So in this case, D2 we thought was southeast side down kinematics. And if that's the case, we should be able to see those cross-girdle fabric, whereas that's a quartz crystal. The long axis of the quartz crystal, the C-axis, is mostly looking at you, and it's on those steronets, and it's forming these cross-girdle fabric. So here, the XY plane, which is your foliation plane, is orthogonal and horizontal with respect to those terranets, and the mineralization is horizontal, so that's X. So we see those nice cross-girdle fabric. However, some of this terranet display quartz grains that are not oriented as you would expect for a monoclinic general shear environment, which means that you need basically to look into the mineralization to see those cross-girdle fabric that we were expecting initially. And the interpretation that we make out of that is that potentially we're looking at a different flow environment, so that the way we interpret the kinematics for these specific specimens is wrong. So we map these specimens with electron backscatter diffraction, and we look at the deformation within those quartz grain, and we calculated the vorticity axis of deformation for the relict and recrystallized grain. And what we found is that while most of the shear zone recorded dip-slip kinematics, so these side-down kinematics, these specific sample recorded some strike-slip deformation. So the takeaway here is that the Eastern Island shear zone was reactivated in a heterogeneous shear environment. So it partitioned two different flow environments within the same structure because it's quite heterogeneous. Now, we also dated the deformation age of that shear zone. We basically threw the kitchen sink at it. So this cross-section here is not a perfect cross-section, it's a composite. So you see 1, 2, 3, and 4. And basically on the map, that corresponds to these portions of a cross-section, 1, 2, 2 to 3, 3, and 4. So we're basically looking to the northeast. And the reason I did that is to display all the location where we dated deformation. So we used uranium-lead crystallization age on the deformed granitoid. We also used uranium-lead on monazite and xenotime and apatite as well. And we also use argon-argon on hornblende, muscovite, and biotite. And the big takeaway here is when we consider only the ductile portion of the shear zone, we have very consistent deformation ages from around 380 to 365 million years old. And then if we look into the brittle portion of the fault, I should say, so the edge of the shear zone, which becomes a fault, so the breccia fabric that I displayed previously, the alteration age or the age for the fluid flow is much younger, but the error is a bit larger, so it's a bit harder to have a takeaway on the formation of these faults. So overall, we've realized that the Eastern Island shear zone was reactivated in the late Devonian with an heterogeneous flow environment. So there's a component of strike-slip deformation and mostly dip-slip, so these side-down kinematics. Now we moved on to the Pocologan Kinebekis shear zone, which is located on the coast of the Bay of Fundy, so in that red square here on the western side. Again, that's an area where we thought the deformation was mostly Acadian, but we quickly realized that it's a bit much younger. So let's look at a transect, which is from A to A prime across the shear zone. And the fabric here and the Pocologan Kinebekis shear zone is listric, meaning that in the core of the shear zone, the fabric is subvertical, but on the coast, it's subhorizontal, and it's cross-cut by normal faults. And interestingly, the fabric is corrugated, so it's folded, and the fold hinge, so the hinge axis is parallel to the mineral lineation overall. So that the dextral strike-slip kinematics is probably related to a component of extension as well. Now, the malonite fabric in that shear zone are absolutely beautiful. It's mostly hosted in granitoids, quartz diorite. So we see a nice progression here across different outcrops from just a foliated quartz diorite to small shear bands marked by biotite grains. And then in the lower left, we start seeing muscovite-rich shear bands and C prime fabrics marked by biotite. And then eventually in the core of shear zone, we mostly see shear bands. A bit of that mineral evolution here is related to fluid flow. So those are composite images built using XRF maps. So on the left-hand side, we have a composite image where the red, green, and blue poles of a pixel are composed of iron, potassium, and aluminum relative abundance. And the right-hand side is just a classified mineral map. I think now that people are using this map tool, those images are much more common. Back in the days, that was a bit more novel. And we see plagioclase grains that are fractured and filled by potassium feldspar. So those are indication that the rocks are not so much in equilibrium during the formation, and it's quite a bit of mass change. So we see that we can characterize that alteration using the change in mineralogy. But the biggest takeaway here is that we also attempted to date that hydrothermal alteration using apatite, uranium lead on apatite, and we got decent ages around 341 plus or minus 16 or 15, 16, up to 313 million years. And we also tried dating the fabric, the ductile fabric, so not the alteration, with argon-argon on muscovite, and got around an age around 370 million years old. And if we look at the deformation age and kinematics of all the structures that I could compile in the Canadian portion of the appellation, we start realizing that several structures were either formed or reactivated during the late Devonian. And my interpretation at the time was that we were dealing with Neo-Acadian reactivation. So I've put the Pokadogan Kinemakesis shear zone here in the red square, but we have the formation of the main Neo-Acadian suture, the Quebec Ridge shear zone here to the right. And we should have the Eastern Island shear zone here further to the right in the Cape Breton Island. So we have a regional pattern, and at the time I thought it was related to a regional deformation event, potentially to the collision of Meguma. So if we look at this ID in map view, we have the Eastern shear zone where we did some of our work in A. We have the Pokadogan Quebec shear zone in B. We think those two structures are relatively synchronous. But we need to have an idea what was before the Neo-Acadian, before the late Devonian, what were the structures that were active before these structures were formed, and what happened then in the late Devonian when what I thought was the Neo-Acadian structures were formed. So here, if you've seen some of my previous talk, I used to call this Acadian structures, but I've come to realize that that's debatable, and that actually that's a really good area for research. So now I'm mentioning it, but I'm calling it before the late Devonian. And we have, for example, the Acadian suture, the Hermitage Bay Dover shear zone that formed with sinistral strikes at kinematics. The Eastern Island shear zone, D1, formed with southeast side up kinematics, and the Belle-Île fault formed with sinistral strikes at kinematics, and that's the structure that's just adjacent to the Pokadogan Kinemakesis shear zone. So if you remember, it's a lot of kinematics, but the big takeaway is that when we reach the late Devonian, the Hermitage Bay Dover shear zone totally changes, it reverses its kinematics. So it's reactivated with textural strikes at kinematics. The Eastern Island shear zone is reactivated with mostly southeast side down kinematics. And then other structures that were already formed, so for example, the Cape Ridge shear zone also has this change, is reactivated with sinistral strikes at kinematics. So I think it was previously a thrust, so southeast side up, with south side up, and now it's reactivated with sinistral strikes at kinematics. And then we form also other faults regionally, like Norimbuga fault, the Catamaran fault, and of course, the Neo-Acadian suture, the Quebec Ridge shear zone with textural strikes at kinematics. So for these structures, we know their deformation age, we know their kinematics, and we can try to put them in a regional shear zone system, but we lack continuity between these structures. It's hard to map it on the field. So how do we get around it? Well, we partnered up with Lyle Harris at ENLS to compile the regional geophysical data and process it. So what Lyle did is that he filtered the magnetic and gravimetric data according to depth based on the frequency and process it so it looks good, like this ternary gradient image. And what's neat with this image specifically is that you can see both the structures and the magnetic properties of the rocks just based on the intensity of the gradient. So for example, here we have the South Mountain batholith, in red, which is a little bit of a positive here anomaly. And then we can see in Meguma the nice, the trace of the hinge of the isoclinal folds. We know they're isoclinals based on field mapping, but you can see the trace of those folds here. We can see beautiful interference pattern in the New Brunswick Highlands and in Newfoundland as well. And perhaps some dikes that are cross-cutting the Bay of Fundy and the Sub-Mountain Batholith, but that's quite debatable because these dikes have never been mapped on the field, as far as I know. And then we've traced those magnetic lineaments by hand, just like you would do when mapping a shear zone on the field or interpreting kinematics on a thin section. And we've extended the trace of the shear zones that we know that are mapped on the field, so the ones that I've displayed previously. And also I did some more structures that were previously unknown. So let's start with something that we know well. There's a cubic wedge Chedebukto shear zone here. That's the Neo-Acadian suture. And using a warming algorithm, you can determine the dip of structures at depth. So for example, the cubic wedge Chedebukto shear zone potentially changes dip direction along strike. If we focus on the Bay of Fundy and areas that I've mapped personally, we can see, for example, that the fabrics are dipping toward the Bay of Fundy, just like we've seen in the Pokadogan-Kinebekis shear zone. And also you can see new structures that are a bit more cryptic. For example, there's a north-south magnetic lineament at the border between New Brunswick. You guys can see my mouse, right?
Yeah.
Excellent. Okay, so there's a north-south magnetic lineament just at the border between New Brunswick and the United States that has sinistral strike slip kinematics. And just the same as the Cape North Fault, which is a map structure that we know formed at the same time period with sinistral strike slip kinematics. And now that we have established that, we can interpret the kinematics just like we do on an outcrop or a thin section. And we can think about this system as a C prime system with some antithetic shear zones. So for example, the cubic wedge Chedebukto shear zone here would be the C prime, so the external strike slip. The Pokadogan-Kinebekis shear zone or the Hermitage Bay Dover shear zone would be the main shear zones. And then we'd have those antithetic sinistral structures marked by the Cape North Fault, the edge of the Norambuga Fault here, just within that square black outline, and also that cryptic structure at the boundary between New Brunswick and the United States. But now that we have added all these lineaments or all these potential shear zones onto our map, now we're lacking age constraints on those. And the way we can get around it is, in the appellation at least, is that we have a lot of cooling edges that allow us to at least test for the potential deformation edges. And I'll show you guys why. So we'll look at these cross sections from B to B prime, E to E prime, F to F prime. So we'd be looking to the northeast. And if we focus on the Cape Breton Island and the Eastern Island shear zone specifically, we see that there's an overlap between the amphibole, muscovite, and biotite cooling edges. So they're synchronous within the shear zone and also in the highlands, which means that because of the different cooling edges of these minerals, cooling temperature of these minerals, we're looking at a rapid exhumation of the highlands. And so basically that indicates that the Eastern Island shear zone was active during the late Devonian, as we know already because we've dated that structure. So you can basically do the same thing here and notice similar pattern across the Guadeloupe Fault. So you can test for the deformation age of these new lineaments that we've added to that regional map. So what we're left at the end of the day with all this work is a regional picture with a shear zone system characterized by this C prime fabric with, for example, the cubic wedge Chedebukto shear zone, which is dextral strike slip, and all these other dextral structure that we've mapped. And those antithetic sinistral structures, like that one that I've mentioned previously, the north-south lineament between New Brunswick and the United States, but also the Cape North Fault. And these structures limit the extent of sedimentary basins that were formed during the same time period, during the late Devonian. So we have the Maritime Basin that was opened. We have the Bay of Fundy that was opened during the late Devonian, and the Nangasset Basin as well, but also the Catskill Basin within Laurentia. and then we can try to find analogous structures that are within active environment, or better characterized, I could say. So the best example we could find to reflect what we see in the Canadian Appalachian is the Nanga Parbat syntaxis and the Mont Saint-Elias syntaxis. So in the Himalaya, and in the Canadian Cordillera, respectively. And what characterizes these syntaxes is a regional shear zone system that was structurally controlling rapid exhumation. So that's characterized with fissure tract dating here in the blue extent, high paleo elevation, and abundant sedimentation. So there's work done by Hillenbrand in the New England Appalachian, where basically you characterize those two last elements, so the high paleo elevation and rapid exhumation. And so that would correspond to that blue extent here. We have the formation of sedimentary basins in the same time period in an active regional shear zone system. So our interpretation, at least at the regional scale, is that we're looking at what we call the Neo-Acadian syntaxis formed in New England with that regional C prime shear zone system with some anesthetic shear zone. And where it comes to online recording, this is where we could cut it, because now we're going to